In this video, we will learn to solve polynomial and rational inequalities. The strategy is that we're going to rearrange the inequality into standard form and then draw the sign chart over different intervals across entire real line divided by the boundary points. The boundary points include the zeros and any undefined x values. Let's look at example for polynomial inequality first. Step 1, we're going to convert it into standard form, meaning that we're going to move all terms to the left-hand side and leave the right-hand side being 0. So first, we're going to use the distributive property to multiply 2x into each of the term inside the parentheses. That's give us 2x squared minus 2x. Then we move everything on the right-hand side to the left. We simplify it. That's give us the standard form. Next, we're going to identify the boundary points. For polynomial inequality, the boundary points are the zeros of the left-hand side function, which is a polynomial function. So we set the left-hand side equals 0. We factorize it. That gives us the zeros being -3 or 7/2. Now we're going to draw the sign chart. We start with a real line and we put down the zeros we determined earlier. So the entire real line is divided into 3 pieces. And we'll put 0 on top of each of this boundary point to indicate these two numbers are the zeros of the polynomial function. So now we need to determine the sign for each of these 3 pieces. To do that, we're going to pick a test point within each of this interval. For example, for x less than -3, we can pick x to be -5 to determine the sign of the polynomial function. Of course, we can do direct substitution. Since this polynomial has been factorized in earlier steps, we can determine the sign of each linear factor and then use the sign of the linear factor to determine the sign of the polynomial. So our linear factor include x plus 3 and 2x minus 7. When x equals -5, each of this linear factor is negative. When we multiply two negatives together, we're going to get the positive. So that's going to be the sign of our polynomial or this interval. So similarly, we can pick a test point for this middle interval to be 0. The first linear factor is going to be positive. The second linear factor, when x equals 0, is going to be -7, is going to be negative. If we multiply these two linear factors together, we're going to get a negative. The last piece, let's pick x equals 5. The first linear factor is positive. The second linear factor is positive. Multiply them together, we're going to get a positive number. So the polynomial inequality is going to be positive over this entire interval. Keep in mind, by intermediate value theorem, if a function is continuous, then it's not going to change sign over this interval. Otherwise, we're going to expect another 0 for the last piece. But this polynomial only have 2 zeros. That means for each of these intervals, we're not expect the polynomial to change sign again. In other words, there should be no further zeros within each of this interval. So with this sign chart, we'll be able to write down our solution. We have to be careful about whether our inequality is a strict inequality or a non-strict inequality. In this case, it's strict, means that the zeros are not part of the solution. Okay, so we only look for the interval where the polynomial function is strictly negative. That's the middle piece with open endpoints. So we write down our solution using interval notation that gives us -3 to 7/2 open at both ends. Next, let's look at another example for a rational inequality. It's going to be similar strategy. We start with convert this to standard form by moving everything to the left-hand side, leave the right-hand side to be 0. To combine the left-hand side, we're going to determine the least common denominator. In this case, it's going to be the product of x plus 4 and x plus 2. So we multiply x plus 2 to both the top and the bottom of the first rational term, and x plus 4 to the top and the bottom of the second rational term, so that they have the same denominator, and we can combine these two terms together by subtracting the numerator. Simplify it further. This gives us this rational inequality in standard form. The boundary points for solutions of rational inequality includes both the zeros of the rational function and any x values where the rational function is undefined. Let's start with the zeros of this rational function. This is determined by setting the numerator equals 0. In the meantime, requiring the denominator doesn't equal 0. In this case, the numerator is negative 2. It never equals 0. So in this case, the 0 does not exist for this rational function. Now let's see whether there's any x values. This rational function is undefined. Now we're going to set the denominator equals 0, because we know that if the denominator equals 0, then this rational function is not defined. This is going to give us the zeros being either negative 4 or negative 2. So these numbers are going to be the boundary points when we draw the sign chart. So let's draw a real line and then put down these boundary points, one being negative 4, the other being negative 2. Again, these two numbers divide the entire real line into 3 pieces. We're going to determine the sign of the rational function for each piece. We don't expect any sign change within each of this interval. Otherwise, by intermediate value theorem for continuous function, we're going to expect further zeros. That's not the case. There's no zeros. So that's why for each interval, either it's going to be negative or positive. There's no sign change. We can determine the sign for each specific interval using test point. Let's pick negative 5 for the first piece. So the term that's going to determine the sign of the rational function includes the factors numerator and the factor denominator. So the numerator is negative 2. The denominator has two factors, one being x plus 2, the other being x plus 4. At this number, the sign of the numerator is negative, and the factors of the denominator both being negative. These three terms will determine the rational function is going to be negative. So for the middle piece, let's pick negative 3 as the test point. Again, the numerator is a fixed number, is always going to be negative. The linear factor s plus 4 is going to be positive. Another linear factor for the denominator, x plus 2, is going to be negative. So a negative term divided by the product of a positive and a negative, that's going to give us positive. So the rational function over the middle piece is going to be positive. The last piece, let's pick x equals 0 to be the test point. Again, the numerator is negative. Both linear factors of the denominator are positive. So if we divide or multiply these factors together, that's going to result in a negative number. So this is what the sign chart looks like. So based on the sign chart, we can determine the solution for the inequality. Again, be careful about whether strict inequality or non-strict inequality. In this case, it's non-strict. That means any zero of the rational function is going to be part of the solution. But in this case, we don't have any zero. We only have undefined x values. That's why we put down circles here at these two numbers to indicate these two numbers are where the rational function are not defined. Now we're going to select the appropriate sign. We're talking about rational function greater than equals 0, and over this middle piece, the rational function is strictly 0. We don't have any point where the rational function equals 0, so the solution is going to be this middle piece. from -4 to -2, open at both ends.